All right. So I will describe the problem called the Capset problem. Right. So a set A of f3 to the n is called a cap if it contains no line. But what is a line? Line is, so this is a finite field of size 3, so it's going to be like A plus B TB, where T is F3, T is F3, and A, B are the vectors in F3 to the n. And B is not 0. Okay, so that's the line. So a set is called the capset. A set is called the capset if it has no line. And well, there's a, I don't know whether you know this card game called the set. Set is a card game where you have a, you have a 4 types of shapes, like for instance, no, is that? I think it's oh, let me look it up actually. Okay, so set is a card game using card like this, right? So you have 4 kind of shapes, right? So either it's diamond, or this shape, and then something like, oops, let me not try to draw it. So you have 4 kind of shapes, and then 4 kind of no, not 4 kinds of shapes. Okay, 3 kinds of shapes, 3 kinds of colors, 3 ways of filling these shapes. Okay? 3 ways of filling shapes, and what else? Yeah, so the color, shape, and shading, yeah, right? Whether it's a stripe or solid, right? Yeah. Oh, no, and number of shapes, right? 1 or 2 or 3. So there are 4 properties. Each of them has 3 characteristics, right? So shapes has 3 shapes. No, number of shape is 1 to 3, and the shape is either diamond or squiggle or oval, and shading is solid, striped, or open, and color is red, green, purple. And then a set is a set of 3 cards, where each characteristic is either or same or different, and that's exactly a line in f3 to the n. So oops, so that set game is to find a line in 12 cards from 12 distinct cards from f3 to the n, right? So 2 players or many players watch the same set of 12 cards, and they each try to find the line. And then once you find the line, you remove all these 3 cards, and then fill in with another set of 30 cards into the table, and then continue. And then yes, and then you may wonder like whether there's any configuration without a line, right? In that case, you cannot have set, right? then usually you add more cards and continue. But at some point you must have a card, you must have a line. But anyway, so that's the set game. So it's related to this definition. So Capset, the special of Capset is a configuration in a set game without set. So then question is, how large can a capset in f3 to the n be, right? Can we construct a large set without any line? And in 1982, Brown and Fuller proved that capset has size little of 3 to the n. Do you know the meaning of little of something? So this means that the size of capset divided by 3 to the n goes to 0 as n goes to infinity. And this work was based on the regularity lemma by Semeredi. And then later in 1995, Meshlem improved it to a big of 3 to the n over n. Right? So this big O notation means when you divide size of capset divided by 3 to the n over n, then this absolute value is bounded by some constant as n, if n is sufficiently large. And this was based on a Fourier analytic method. And then 2012, right, Bateman and Katz and Princeton proved highly sophisticated method to prove that it's at most 3 to the n over n to the 1 plus epsilon. So this little epsilon, they made a lot of Fourier analytic argument and spectral argument, and this is highly complicated. So that was the status until 2016. There was a big breakthrough. And everyone was surprised, actually. And everything happened so quickly, so let me describe the story. So we even need the dates. Like so on May 5, 3 mathematicians, Ernie Krut, and then Lev and Peter Pak, posted a paper on arXiv proving that a subset of not f to the n, f3 to the n, f4 to the n without a 3-term arithmetic progression So it's not a complete line, but it is like just 3 points in the vector space, right? So the middle one is the average of the other two. Right? Has size at most big O of 3.61 to the n. So it's improvement over 4 to the n. Now, but this was not about f3 to the n, but soon. So this was only on arXiv. So arXiv is a website where people post the manuscript, which will not even refereed, right? So the first draft is usually on an arXiv. It's not really checked, but that's the place where, as soon as I approve some paper and ready to be submitted, I will post it on arXiv so that people can see. And then on May 12th, John Ellenberg noticed that their argument can be modified to prove. I mean, oh yeah. So what happened precisely was, Ellenberg posted on the blog saying that, oh, this paper is interesting and they have great ideas. And then on May 15, Ellenberg realized that this, I think it's, so he posted a blog article on the blog saying that a capset in F3 the n has size sub c to the n for c big less than 3. So this is a big improvement, right? People try, so far all the normal method was only improving this a little bit, right? So still this exponential part was same, 3 to the n. But suddenly Ellenberg was able to observe that by using their their method, one can prove the solve the Capset problem with a way better bound. And the proof was so simple, it was like very short PDF file. But then in the blog article, somebody commented, and anyone can write a comment in the blog, and Gizrick wrote in the comment that he also made the same proof, same observation. And then they decided to write a joint paper. So they posted, so Ellenberg and Giswit posted the archive paper on May 30. So everything happened within 1 month. So after, of course, they must have spent a lot of time making this, but after that the paper was posted, everything else was happened very quickly. And they prove that every capset has size at most little O of 2.756 to the n. And this was the first non-trivial exponential upper bound. And they not only solved this capset problem, but they also solved the more general problem with the other field as well. And this was published in Annals of Math in 2017, right? And it had only 4 pages, right? So we're gonna see the proof. All right, so let's Q be the let F be a finite field, and Q is the number of elements, and Mn be the set of monomials, x1 i1, x2 i2, xn in, where each i1, i2, all these integers are at most q minus 1 and list 0. Okay, that's Mn. And let Sn be the vector space of polynomials with variables x1 up to xn. So this is okay, let me just say a subspace a subspace of polynomials with these n variables whose coefficients are from this finite field, and it's spanned by Mn. And let's say S and D is the subspace of Sn consisting of polynomials of degree at most d. Okay. So let me explain a few lemmas. So F is finite field, and A is a subset of F to the n, and F is this polynomial of degree at most d, where each monomial, each variable has degree at most q minus 1. Right? Now, if f of a plus b is 0 for all ab in A, then the number of x in A with f of twice x is non-zero. So what is twice x? It's x plus x. Oh yeah, when twice x is defined, right? F of twice, yeah. Right. It's m most this number, twice, right? So twice the number of monomials. Oh yeah. So what is this? M and D. Okay, let me. So M and D is the subspace of Mn. I mean subset of Mn is a subset of Mn consisting of monomials of degree at most d. All right, so let's see why this is true. Right, so we have a polynomial, and no matter how I choose two distinct elements, the one more thing is not 0, then number of x is twice not 0 is bounded by something. So let's think of f of x plus y, right? And if you expand it, then it will become a sum of monomials, right? Sum of monomials where mx, m prime is not a derivative, so m and m prime are the monomials. Okay, let me just say these are the monomials in M and D, right? And there are some coefficients, but let's not worry too much about coefficients. Oh, but the okay, let's write coefficients. C m because I may need a 0. We may, so by expanding we have these equations, right? Like for instance, x plus y squared. No, right? So x1. Let's say x. If I have x1 plus y1 squared, then I expand it. I would have x1 squared plus twice x1 y1 plus y1 squared, and then it completely expanded. Eventually, each monomial is product of x variables and y variables. Now, the thing is, the whole thing has degree at most d. So either m of x has degree at most d over 2, or m prime of y has degree at most d over 2. So for each summand, either m prime x has degree at most d over 2, or no, m prime y has degree at most d over 2. So let's rearrange then. So f of x plus y is sum for all monomials of degree at most d over 2. We have sum mx times some polynomial, right? So I collect the same term over here, plus all the monomials of degree at most d over 2. Then you have my times I have collected all the terms. Let's use g, not y, x. All right. So these are the some of these, some of the CMM prime, m prime y, and this is some of the CMM prime mx. Yes. All right. So that's the f of x plus y. Now we're gonna construct a matrix. Huge matrix. So that B be an A by A matrix. Right? So that whose AB entry is f of A plus B. So this AB entry, BAB, is f of A plus B. So this is again, I can write it as MA FM B, right? Plus, so this is M for all monomials of degree at most d over 2, where each variable has all degree at most q minus 1. And let's change m prime as m. So m is in m d over 2, and I still have the same thing. So m y, no, not y. It's okay. G m a and m b. Right. How do we obtain? Well, you have indexed by these monomials of degree at most d over 2, and the rows are indexed by A, right? And then we make a product with another matrix whose rows are indexed by M and d over 2, and columns are indexed by B, right? That's the first entry, and the second entry is similar but transposed, right? So the This is indexed by m and d over 2, and this is indexed by a, and this is m and d over 2, and this is b. Now, how do we determine this matrix? Okay, how do we determine it? So, why is this true? First of all, if you look at the AB entry, so what is AB entry? So rows of A, right? So BAB, so this times that is going to be the AB entry. I mean, this row vector with that is AB entry, and that is precisely this summation. All right, now what is the rank of this matrix? What is the rank? Yeah, but what's funny here is that look at all these row entries are looks like MA, right? This is MA, and what is the rank of this? Right, so right, I mean, the thing is, so this part has rank and most number of these, I mean, number of columns, right? So that means, remember, if you have two matrices, rank of PQ is the most rank of P. So B, so that means this part has rank and most M and D over 2, and similarly this part has rank and most M and D over 2. So it's two matrices of rank and most that, and the rank of A plus B is and most rank of A plus rank of B, right? Because remember, rank is depends on the column space. So if I have and the column space of A plus B is spanned by the column space of A plus column space of B. So therefore, rank of B is at most twice this. All right? Now, why is this useful? I know that f of A plus B is 0 for all distinct AB. In A. So what does that mean? So that means this matrix B so B is indexed by A and B. And if it's not on the diagonal, everything is 0. All right. So that means B is a diagonal matrix. So the rank of B is equal to the number of non-zero diagonal entries. And I know that rank of B is at most twice mn d over 2. Alright? So that means the number of x in A with f of twice x non-zero is at most twice mn d over 2. Alright, so that's the proof of the lemma. So we're using the inequality on the rank. Alright, so how do we use that? So this is a proof by Ellenberg and Kiswit in 2017 paper. The manuscript was posted on 2016. So we have a set A, which is subset of, and the subset of f to the n, where f is a finite field. And if, yes, I want to say that if A has no 3-term arithmetic progression, so what does that mean? In other words, whenever A1 plus A2 is equal to twice A3 implies and A1, A2, A3 are in A. If this implies that A1 and A2, A3 are equal, right? So we, of course, we have to allow the arithmetic progressions which consist of the identical terms, but except that if there's nothing else, then size of A is bounded by 3 times m and q minus 1 n over 3. All right, let's prove this theorem. So I'm going to choose D later. It's going to be some number less than or equal to q minus 1 times n. It's positive. And we will define a vector space V. So define V as the subspace of SDN, so which is the subspace of polynomials of degree at most d, where each xi has exponent at most q minus 1. So this is spanned by mdn, right? Anyway, subspace of that vanishing on the complement of 2a. So in other words, so V is the set of vectors, set of polynomials in SDN where f of x is 0 for all x not in 2a. So 2a is the set of twice values of a, right? So 2a is twice x. So what is the dimension of V? Dimension of V is at least dimension of the whole space, which is dimension of S and D minus the cardinality of the set minus the f to the n minus twice a. Right? Why? Because think of the linear transformation. Think of the linear transformation from S and D to f to the fn minus 2a, right? Mapping f to the collection of fx where x is not into A. This is a linear transformation, and the corner of this is the V. And dimension of this, dimension of that is, of course, at most this much, q to the n minus twice A. So dimension of V is at most dimension of that is m and d minus q to the n plus 2A. Right, but 2A, size of 2A, well, same as A. Let's assume that size of Q is at least 2. I mean, not 2. So the size of field is, I mean, it doesn't make sense if the field has size 2, right? It doesn't make sense. So let's assume the Q is bigger than 2. Right. So this is one inequality that we have. Now, I want to say like, I want to talk about the size of A, I mean twice A in some sense. So let's look at the following. So if I choose A, B, and these things, A, B are in A, then f of A plus B is 0. Why? Because this implies that A plus B is not in A. More precisely, A plus B is not in 2A, right? Because if A plus B is in 2A, then A plus B is 2 times something. A plus B is 2 times C. Then A, C, B is an arithmetic progression of length 3A. So it's 3 times arithmetic progression. So therefore, A plus B is not in 2A, and if f is in V, then f of A plus B is 0. All right. So whenever you have distinct A, B, and A, then f of A plus B is 0. So by the previous lemma, the number of x in A such that f of twice x is 0, non-zero, is bounded by twice m and d over 2. Okay. For every f. Now, let's choose a function. So choose f so that the sigma, which is called some support, so which is so the number of points where f of x is non-zero is maximal. All right, and now I know that f of x is 0 if x is not in twice A, right? This is because of the construction. Choose f in V. F is in V, so outside of 2A, it's 0. So how big is the sigma? Right? See, the size of sigma is like it's twice x. It's x in f of n, where f of x is non-zero, but the only place it could be non-zero is when x is twice of something. So let's say y, twice y, or f of twice y is non-zero, right? But the number of them is same as y and f of them, where f of twice y is non-zero. And this is at most twice m and d over 2 by the previous lemma, or by this statement, right? So the size of sigma is bounded. It's small. Now, but I chose sigma to be maximal. And the claim is, right, so we claim that size of sigma is at least dimensional of V. If not, what does that mean? Then there is a non-zero polynomial in V such that the image g x is 0 for all x in sigma. Then let's say p, so let's say I have f and I have g, right? Then the sigma, let's say sigma prime is the set of x where set of vectors in f of n where fx plus gx is non-zero. Then sigma prime is strictly bigger than sigma. It contains all sigma and it contains more, so the contradiction to the right, so the f of g is in V, right? The contradiction to the choice of f, right? We could replace f by f plus g. So this implies that the dimension of V is at most twice m and d over 2. All right. Now we are ready to plug in the inequality, right? So let's look at this inequality on the left hand side. So therefore what we get is m and d over 2 twice is bigger than m and d minus q to the n plus a, right? And that gives an upper bound on the size of a. It's twice m and d over 2 minus, plus q to the n minus m and d. All right. So let's see what's happening. So what is a q to the n minus m and d? What is this value? Right. Right. So q to the n, you can think of it as a number of monomials of degree number of monomials, number of it's number of monomials. Remember, do you know this fact? X to the q is x in the finite field, right? So you don't need the q's power. So therefore, like think of the x1, i1, x2, i2, xn, in, and then we only need to worry about the case where each I1, I2 are the numbers between 0 and q minus 1. So the number of possible values is q, and you have n values to fit in. So that's q to the n, and we are subtracting m and d. So these are the number of monomials of degree at most d, right? So q to the n minus m and d is the number of monomials x1, d1, x2, d2, xn, dn, such that d1, d2, dn are at most q minus 1 and is 0, and their sum is at least d plus 1. Now, by symmetry, that's same as number of monomials x. Now I'm gonna replace it by xn minus d1. No, not n. Okay, so q minus 1 minus d1, x q minus 2 minus d2, xn q minus 1 minus en. All right, and then q minus 1 minus d1 is still between 0 and q minus 1, and their sum, right? So their sum, so q minus 1 minus d1 di, if I sum up, that's q minus 1 times n minus sum of di, and this is at most q minus 1 minus d minus 1. Wait, do I have a minus 1? Yes. Therefore, this is same as m and q minus 1 n minus d minus 1. Is it clear? All right, now, so what do we get? So this implies that size of A is less than or equal to twice m and d over 2 plus m q minus 1 n minus d minus 1. Okay, now what will be the best thing? So how are we going to choose d? Well, let's choose d so that d over 2 is equal to q minus 1 minus d minus 1. So this is same as like 3 over 2, d is equal to q minus 2. So d is equal to 2q minus 2 over 3. Am I missing n? Yes, there's an n. Okay, let's change the q minus 1 n minus 1, so it's 3q minus 1 n minus 1 divided by 2. All right, I mean it's less than 3q minus 1 n over 2. Yeah, let's simplify. Let's ignore minus 3. So then size of A is less than or equal to twice. So if I use this d, if I use this d, this particular d, then both of them will be equal. So it's going to be 3 times m and d over 2. Now if I ignore that, yeah, so this is 3 times mn, and now d is this value, and oh no, I that's a mistake. 2 2 3, right? And I'm dividing my 2, so it is cube minus 1 n over 3 minus 1 over 3. But anyway, let's ignore 1 over 3. So mn q minus 1 n over 3. All right, so that's the size of A, the upper bound of the size of A. So now we are really ready to prove the Ellenberg and Gieswick's theorem. Right? So if A is a subset of f3 to the n with no 3-term arithmetic progression, so if A is a capset, then size of A is less than or equal to 3 times n, where n is this gigantic sum n factorial of A factorial B factorial C factorial, where A plus B plus C, so A, B, C are non-negative, is n, and there's A plus B, no, B plus 2C is less than or equal to 2n over 3. And furthermore, n is a little 3n is little of 2.756 to the n. Right? So this proves a theorem way stronger than previously known theorem. Here you have only 3 to the n, and 3 is some of the obvious bound, and they made a lot of effort to improve it slightly, only by n to the 1 of 1 plus epsilon. But now we have a completely different growth rate. Right? Instead of 3, now we have 2.756. And why is this true? By the previous theorem, we can take n to be, and I mean, if I take previous theorem, now take q to be 3, right? If you put q to be 3, then you're going to get is 3, m to 2n over 3. So what is this, right? So this is the number of solutions of this equation, dn. Their degree is at most 2n over 3, right? And each di is 0 or 1 or 2. Right? So remember x1, d1, x2, d2. If we have a monomials like this, and each di is no more than 2, right? Because it's a finite field of size 3, so you don't need the x to the cube. I mean x to the 3. You don't x cubed is equal to x. So what is it? Well, now this is same as number of solutions of 0 times A plus 1 times B plus 2 times C. So I'm counting number of A's, number of B's, number of C's, right? okay, what is the best way? So if A is the number of zeros and B is number of ones and C is number of twos, then we want their sum is at most 2n/3, and the total number of them is exactly n, and each of them is at least 0. Then once you fix number of a's, number of ones, number of zeros, number of twos, then what's left is n factorial of a factorial, b factorial, c factorial. So this is exactly n. So that's the upper bound. Now, how do we get 2.756? This is where we're gonna use a polynomial. Think of the following polynomial. 1 plus x squared, and take n's power. Now, what's going to happen? Right. So this is the same as 1 plus x squared, 1 plus x squared, 1 plus x squared. Right. Now, look at the coefficients of x to the, if I expand it, right, so it's like sum of something times x to the I, where I is from 0 to something. And if this number is, for instance, if this number is, if I is some number, then the coefficient is the number of ways to make that I by choosing certain number of x to the 0, certain number of x to the 1, certain number of x to the 2. Right? And then you can see from this observation that, right, so like, yeah, this is something like this, right? So a plus b plus c is I, and a plus b plus c is n, and b plus 2c is I, and then n factorial over a factorial, b factorial, c factorial times x to the I. That's the expansion. So take x to be some value between 0 and 1, and then if we divide both sides by x to the 2n/3, then what you get is something like this, right? So b plus 2c is I, and a plus b plus c is n, and I is from 0 to something, and x to the I. Now, x to the I minus 2n/3. And since if I is smaller than 2n/3, then this number is going to be bigger than or equal to 1. And if I is less than, if I is bigger than that, then this number is x to the something, which will be extremely tiny, but still positive. So I will ignore all these remaining thing. If I is bigger than 2n/3, I'm going to ignore this term because this is small number. So that's why we have an equality. If I is less than 2n/3, I will replace this by 1 because x to the some negative something is going to be bigger than 1. So this whole thing will be bigger than n, right? Is it clear? So this is from I0 to 2n/3, sum of n factorial, a factorial, b factorial, c factorial, and a plus b plus c is n, and b plus 2c is I, and this is equal to n. All right, so now we have an upper bound. So n is less than or equal to right, so let me compute a little bit further. So x to the 2/3 plus x to the 1/3 plus x to the 4/3 to the nth power. All right, this is true for all x between 0 and 1. Now, what I'm gonna do is to choose x to minimize that. How do I minimize this? Well, think of the f of t as the, so t is gonna be x cubed, x to the 1/3. So minus t squared, no, t to the minus 2 plus t to the 4. That's my f of t. Then that's derivative is minus 2t minus cubed and plus 1 plus 4t cubed. Right? So when is it minimized? So if t is 0, if and only if minus t minus 2 and t cubed plus 4t to the 6 is 0. Right? So right, so now 4 so when is it minimized? Well, I can solve it. So t cubed is something like 8 and minus 1 plus minus square root 1 minus 4 times minus 2. Well, is this best possible? And then I have to have, all right, let me go back. Let's not take f of t like this. Let f of x to be x to the minus 2/3 plus x 1/3 plus x to the 4/3. Then what its derivative is minus 2/3 x to the minus 5/3 plus 1/3 x to the minus 2/3 plus 4/3 x to the minus 1/3, right? And now if I arrange terms again, then what I get is x to the minus 3 to the 5 times minus 2/3 times plus 1/3 x plus 4/3 x squared. Okay, that's a lot better. So minus 2 plus x plus 4x squared. And then if you solve it, so f derivative is 0 if and only if x is right, so 8, so you have a minus 1 plus minus 1 squared minus 4 times 2, 32. Oh, but plus 32, right? So it's minus 1 plus minus square root 33 over 8. But we want some number between x and 1, between 0 and 1, so choose x to be minus 1 plus square root 33 over 8. In this case, f of x is roughly, if you use computer, we get 2.75510. So that means, this means that n, not n, that means n is less than or equal to little of 2. And well, if I do this, so let's put 3, and instead of what 755, what was 756? Now this number 2.756 is strictly bigger than 2.75510, blah blah blah. So for large n, this inequality is definitely true. Okay, so that's it. That's the proof. And I mean, you can put, of course, you can put the little of that. All right.